All right, folks, we're going to do another day with linear regressions just so we can get a little bit more practice with how to use our calculator to talk about line of best fit. So we're starting out just like last time with a table of values here, and we want to decide of our two values which is the independent variable and which is the dependent. So reading through here, it's got the total cash income for farms, and it looks like it's representing the years from 1990 to 2007. So again, the easiest way to tell here is just to go by what it sounds like out loud. Think about, would the amount of income depend on what year it was, or would what year it was depend on the amount of income? Okay, and it makes a lot more sense that your cash is going to be determined by what year it is, what's going on with the economy, and all that stuff. So just like we're used to seeing, our year here is our normal X value, which we're going to put always in list 1, and our amount is our Y value, and that's going to go in list 2. Now you'll notice, and this is something we have to pay attention to here when we go down to write our equation, they assign variables, which means when we write our equation, we cannot use X and Y. We have to use the variables they gave us. Okay, so what I'm going to do right now is pause the video to give you some time here to be able to type this in your calculator. I am going to warn you though, sometimes with years here, they give you some special instructions. With years being the way they are, numbers are large by default, so sometimes they have us change the year and not put in all 4 digits, but only some of them. So right here, it has underlined, let the independent variable be the number of years since 1900. So I don't want to type in 1990, I want to say that's 90 years after 1900, and so on. So this would be 95, then 100, 104, 105, 106, and 107. Okay, so pause the video and take care of that. Put in list 1 items and list 2 items, and then we can chat about the rest here. Okay, I've got my items in my list. Hopefully you have the same here. You want to make sure you always double check them that they match up, again, with those smaller numbers here. And what we're going to do is calculate our regression. Remember, the steps for this are on your blue note card, so it'd be handy to have that out. Okay, but just like we did last chapter, we're going to statistics there, stat, over to calculate. And we are in this regression section here. We're talking about lines, so it is number 4. Everything should be set up there, list 1 and list 2, so you're good to go. And we have all these items here. Remember, if you don't have R, you need to make sure your diagnostics are on. You can go to your catalog to turn them on. Okay, diagnostics. But we see these here. We're going to answer A and C. I skipped over B on purpose because all of these items are right here already in our calculator. Okay, remember, for these line of best fit, we're going to use 3 decimals always. Correlation coefficient, because they all look pretty similar, you'll see that as we go through different examples here, we're going to use 4 decimals for those. Okay, so what I want you to do is go ahead and jot those down for me. And then remember, when we're talking about our line of best fit, normally we follow the equation here, and they use Y and X just like we normally do. But our A value is our slope, and our B value is our Y-intercept. We're going to use, instead of Y and X, the variables they give us. So instead of Y, we're going to start with A is approximately. Plop in your number. Then instead of X, we're actually using Y to talk about year. Okay, make sure that you say approximately anytime you're rounding, and our R value to 4 decimal places is at 0.9607. Alright, we're going to talk just a little bit about what all these things mean. Okay, our slope here is specifically a positive slope, and that just means as time goes on here, we're increasing our cash income. Okay, it is going to ask us to be more specific than that sometimes, And remember, you want to include details like labels, so this would be 6.789 billions of dollars, and then per 1 year increase. Our y-intercept here is a negative value, which would mean at time 0 or year 0 for us, we would have negative cash income. Well, that's because 0 is so far from the 90 that we typed in, 1900, that it's not making a lot of sense. Okay, remember, outside of those given values aren't necessarily as accurate. We're going to use this equation to go ahead and do some calculator work with some questions here. So going back to part B here, it's asking us to look at the 2000 cash income, and that's directly from your table. It's just repeated. And we're supposed to find the error in that value based on what our model says it should be. Okay, so the observed value is literally what came from the table. It's approximately 313.4. That's what they told us right there. Okay, remember, even if it doesn't say about here, anytime you're talking about billions, it's a rounded number, so approximately. Our predicted is coming from our calculator itself, and we just have to trace that value that goes along with 2007. Okay, we didn't use 2007, we used 107, so that's something we have to be careful of when we trace that. Okay, so let's go talk about how to put this thing in our calculator so we can take care of this. Go into our y equals. This is, I think, step 4 on your blue note card to paste it in here. We already calculated the line, but we have to make sure it shows up here. So hitting vars where all of our information is stored, we go to then statistics. And along the top you see equation. We want to plop over to that and hit that regression equation. That'll bring the whole thing up for you. We want to make sure that our graph plots are on. Okay, you can see them highlighted there, but you can always go back to your second y equals to make sure they show up as well. Mine are on, and it's got the scatter plot that we want. And then zoom 9 is going to make sure that my window is appropriate for the points that I put in. And now that that's taken care of, we can go ahead and trace that x equals 107 like we were talking about. Okay, remember, your plots are going to be up first. I've got my cursor highlighted on those points, but if I'm making a prediction, it's on that line, so I need to get down towards the line. Once you're on the right thing, it'll actually show up top there, and then we just type in our 107. Okay, remember, our y values are talking about money, and they're talking about it in terms of billions of dollars. Okay, we want to round to the same thing that they did up here, which is 1 decimal place. So that for us will look like 292. So about 292. And I'm going to put the 0.0. You don't have to. Okay, let's go ahead and put our billions on here. In general, when I'm talking about error, I won't actually have you put these things in a blank. I'll usually just ask for the error, and we know those are the 2 things you need to use to find it. All right. In alphabetical order, error is observed minus the predicted. So we just have to go and subtract those 2 things. So just in your calculator, type in your 313.4 minus your 292, and we've got about $21.4 billion of error. Okay? And so that, in terms of when we think about it, of billions of dollars, that's quite a bit of error. Okay, when we compare it to our total cash incomes and kind of relate it to the size, it's not necessarily the worst. If you go back to your graph, if we're thinking about where that 107 shows up, let me just bring it up again. This point right here compared to the dot on our graph is one of the furthest away points in terms of our line. So this error was bigger in terms of all of our other values that actually showed up. And generally that happens as you get towards the end of your values, because you're talking about your line trying to fit the most points, and sometimes at the ends it gets less accurate. What we're going to do now is talk about this number in terms of accuracy of the model. So remember, your R value tells you two things. The sign tells you what our slope is doing, and the value tells you how linear your points were. Okay, I'm going to remind you of the little number line we made last time. -1 and +1 are perfect, and 0 is not linear. Not necessarily that your model or your points can't be modeled, but they probably shouldn't be modeled with a line. Okay, so what we're going to do is talk about this. It says just talking about the appropriateness, so that means size on this number line, closeness to 1. So it looks like 0.96 is fairly close to 1. Okay, I did mention last time that we're not going to see something super low when I give you points here. So anything above 0.9 is decent. Doesn't mean it's perfect, but when we look at our error, we can go from there to kind of decide whether it's the best line or the best model, or if we can maybe come up with something different as we go through different functions here. So since our R was relatively close to 1, a linear model is appropriate. Okay, if we see under about 0.9, then maybe something else might be better. We will, throughout this chapter, compare different models to decide which of our parent functions that we've been talking about this chapter so far might fit data better, again, looking at the shape of our points. Now, again, let's talk really quickly about the other thing that the R value can give you. It's not asked for here, but just as a reminder, okay, if our R value is positive, that tells us our slope is positive. And in terms of context here, we would know as the year increases, by 1, we would say that the cash income also increases. Okay, you're going to, on the next example, see specifically when I ask you about the slope number, and that's when you want to involve the actual value that for us this time was that 6 and some change. All right, next thing we're going to look at is the center of gravity. That's on your note card, both what it is and how to find it. Okay, so we want the x bar, y bar. That's the mean of the x values and mean of the y values. That can be found in your 2 variable statistics. So we want to go stat, over to calculate, and the second option down there. Hit and enter until something pops up again. And we're writing this as an ordered pair. Okay, so we've got the 101 here, and then you may have to scroll a little bit to find the second one. Okay, in general here, this one is one of the examples where I don't really care what you round to, and because it's an ordered pair, I don't care much about labels. What we're going to use this for is always a proof of just showing that the line of best fit has to have this point on it. So actually, the more decimal places you use are better here to get it to round to a more appropriate value. So 101 is already nice. It's talking about the year 2001. but our second value has a lot of different decimals on it. Our table rounds to 1 decimal place. You're okay to put extra if you want here because I'm not going to take off for rounding. So here, 251 point maybe 2. Okay, we'll say we rounded, but labels aren't important because we're going to use it to test our line of best fit. So what I need you to do, remember our steps here. We are going to first write the equation we came up with. Okay, so remember they said A is approximately, and then it was 6.789. And then our Y value minus 434.454. Double check that I remembered that right. Good. And then step 2 is we plug in that point. So X value goes here, Y value goes there, and we're just going to see how close these numbers are. We may have some rounding error because, again, we didn't put all the decimal places that really went with that Y value. So step 3, we'll actually see how close it ended up being. Just substituting in. Your last step, we already have a nice number on the left. You just have to type the right-hand side of that equation in so that we have something to compare it to. So 6.789 times your 101, then minus 434.454. So here, if we round to the same thing we did up above, it does end up rounding to the same value, which is nice. The whole goal is these are supposed to match. Again, because of this approximately, it may not be perfect. So if you get a decimal place off here, as long as it's pretty close, that's okay. Rounding may cause those to look a little bit different, even when you are in that last step. Alright, then we're going to do a couple estimations back with our line and compare them. So from here, we're taking and looking at 2005 and 2012, changing them to the X values that match from the table. So this would be 105, this would be 112, and then again, X values just mean tracing in our calculator. So let's take care of that. Go back to our graph, starting with the first one here, 105. Make sure here that your line is showing up. 105, enter. 1 decimal place because that's what our table tells us to do, and we want to put labels on here. 278.4. And that's billions of dollars. Doing the same thing for 112. Remember we talked about this error last time. When you see an error, use the go to. It tells you what's wrong. Hit enter. It says the 112 itself is wrong. We saw that happen last time. Sometimes we are asked to find a prediction that is not in this window. So we're going to adjust our window to make sure the number 112 shows up. Looks like the problem is our X maximum isn't big enough. So we'll just change that to maybe 115. Hit graph. And then when we go to trace, making sure our line pops up, the 112, we shouldn't have any issues. So 325.9. Making sure we put billions on there. Okay, now I want you to think about this next question. Which estimate from up above would be more accurate and why? It may help to look at our picture. So our 112 is over here versus our 105. I'll bring it back up. Is over here. Remember what we talked about last time. Our line of best fit is determined by these points we're given. From here our lowest x value to here our highest x value. So inside, our line of best fit should be more accurate than outside where our points don't exist. So we're going to say the estimate from 2005 is more accurate because it was between the given x values Another way to say that is it was interpolation. Okay, shorter, but you have to know some vocab. So you can say the estimate was more accurate because it was interpolation, whereas the estimate for 2012 was outside of given x values. And the vocab for that one is, you could say, whereas the estimate for 2012 was extrapolation. Okay, I do want you to mention both, because you could have a situation where both of your estimates are interpolation, and if that's the case, then you would have to go look at the residuals or the error to be able to determine which one was more accurate. Okay, if one is interpolation and the other one isn't, automatic, the one inside is going to be more accurate. Okay, we're going to do one more example here. This time I'm going to let you do most of this on your own, and I'll check in here every once in a while. So what I want you to do right now is pause the video and take care of A, B, and C on number 2. Make sure you type in your data carefully, and then we'll check back after you finish those items for me. Alright, first thing, making sure here you want to decide which one are independent and which ones are dependent. That's always step 1. Don't assume that the top one is X. In this case it is, but the reason is because we're talking about breaking strength for this rope here, and we want to know, would the diameter of the rope determine the breaking strength, okay, or the reverse of that. Okay, use the word depend and it'll help. Would the diameter depend on the pounds it can hold, or would the pounds it can hold depend on the diameter? It makes more sense that the diameter is going to determine how much it can hold. So here's our dependent, our Y value. Here's our independent, our X value, list 1, list 2. Okay, and you'll notice as the diameter increases, the weight that the rope can hold before breaking can also, or is also increasing. So we do have a linear positive relationship here. Our line of best fit ended up being a slope of about 502. Y-intercept was negative, but again, sometimes that happens when you go outside of the window that we're given here. When we're talking about error, you want to do the observed first minus the predicted. I rounded to a whole number because it actually looks like the table is rounding to the nearest 5, but whole number is pretty good here. There is a possibility for negative error. It just depends on which one of these values is higher. Okay, we care about the size, not necessarily the sign. And it looks like if we were comparing these, just to kind of talk about what we mentioned on example 1, if I wanted to know which prediction was more accurate, the one for the 12 millimeter diameter rope or the 18 millimeter, I would say that the 12 millimeter prediction was better because 88 is not as much error as 772. Okay, so you can compare those residuals to also think about accurateness of your model. Okay, here when you're looking at these, you probably had to adjust your window for this 25 here because 18 is the highest. So if you got an error, remember that's how you fix that. And we're going to talk a little bit more on accuracy and what correlation coefficient and slope mean in terms of what I want on each parts of these. Okay, so D, E, and F, I want you to pause the video and try out, and then we'll talk about G together. All right, so again, we're going to say the estimate for, this time we're talking about breaking strength of a rope. Okay, the estimate for that is more accurate because it was interpolation. Again, you can say between given X values instead. Does not matter to me. Then it said the compared to the estimate for the 25 millimeter rope, which was extrapolation or outside of the given X values. You do not need both of these things. Pick your favorite version. You will need to know what interpolation is when you see it, but when you are writing it, you have the choice there, either or. It looks like this R value compared to our last example, this one is more linear. Okay, our line of best fit the points better than the last example because that one is closer to 1. So that's what we're talking about on part F here. Since the R value is close to 1, a linear model is appropriate. Again, this was not asked, but just in case when you're working on your homework you see something like this, we can also tell, because R is positive, that the diameter of the rope as it increases, so does the breaking strength in pounds, or the amount of weight that rope can hold. Alright, here's what we're going to talk about last. It says, what does the slope of the line of best fit indicate? So first thing I want you to do is write down the slope. That comes directly from our line up above. And average rate of change we want to talk about on average. Slope is on average what's happening here. Okay, then all you have to do is mention the two variables that we're working with. Ours is the diameter of rope in millimeters and the weight that the rope can hold, or the breaking strength in pounds. And we're going to mention those two things with this number. So because positive, we're going to say as the diameter of the rope increases by 1 millimeter, the amount of weight the rope can hold, or you can say the breaking strength, increases by about 502 pounds. In this sentence, I don't care what you round to. Okay, our equation used 3 decimal places, but when we talked about pounds before, it was whole number. Does not matter to me. Okay, so those two items. It also can be flipped around, just so you're aware. You could say, on average, there is a 502 pound increase in breaking strength for every 1 millimeter increase in the diameter of rope. Okay, so order doesn't matter on those types of things. You just got to include the details with the labels. All right, if you had any trouble with calculating any of these examples that I just went through pretty quickly here, please come see me. If you have any calculator issues, errors that you can't fix, send me an email, and usually I know the problem.